In chapter 23, section 3 is really short, and all it does is talk about the different kinds of boxes and the different kinds of standard errors. So we've basically limited ourselves to two different boxes. Boxes that have ones and zeros, and we've decided that percentages are the best way to deal with that. So we would say something like 0.82 ones and 0.18 zeros. How do we calculate the SD of that box? We do the shortcut, which is this, and it's really 1 minus 0, but we skip that because it ends up being 1 every single time. So it's simply the square root of 0.82 times 0.18, which is really nice. What is the expected value for that box? 82%, which is really nice. The other box has numbers in it. So we could have, say, 1, 2, 3, 4, 5, 6, 7. Okay. Now, with this box, we can do two different things. We can either calculate the sum of the draws or the average of the draws. Okay. The sum of the draws is simply the average of the box times the number of draws. So the average of this is 4. So my average of the box is 4. If I do 100 draws, then I times that by 100, and the sum of the draws is expected to be 400. Okay. What is the expected value for the sum of the average of the draws? It's just 4. Okay. So those are the three different things we've calculated. Sums and averages come from a numbered box. Percentages come from a 0-1 box. And essentially, those are yes and no questions. Do you like your mom? Yes or no? Right? As opposed to, how many siblings do you have? Which would be a numbered box. Okay? And it turns out that the sum of the draws isn't really particularly useful. Because if I'm in a county, we have what, 10,000, 11,000 people in the county, and I wanted to know information about the income of this county, I'm not going to run around and ask people how much they make and then add that all together and say, hey, 500 people made $17 million. Right? That number doesn't really do anything for us because the more draws we make, the higher and higher it gets. So we really rely on the average of the box. But the question is, how do I get the SD of a numbered box? I have to use my stat. And it turns out in this case it was 2. It was what we did yesterday. Okay. Now, there are 3 different standard errors. The first one is standard error for number. Which one of these 3 expected values, so this one, or this one, does SEN apply to? The 400, the sum of the draws. And that is calculated by taking the SD and multiplying it by the square root of the number of draws. So in this case, it would be 400 plus or minus 2 times the square root of 100, which is 10, so 20. If you roll a 7-sided dice 100 times, you are expected to get 400 points plus or minus 20. Now that's a probability. You have a 68% chance of doing that. Okay. How do we calculate standard error for, let's do percentage. Which one does this apply to? The 82%. Okay. And to calculate that, I do the SD of the box and I multiply that by the square root of the number of draws, and then I divide it by the number of draws, which is how the book always lists it, but we're smarter than that. We've done the shortcut, which is just the SD divided by the square root of D, because the square root of D over D is the same thing as just 1 over the square root of D. Okay? Now, there's another SE that I'm missing. What's it called? SE for average. And the SE for average ends up being exactly the same thing as the SE for percentage. So I can take this 20 and divide it by the square root of 100, and I get 2. So plus or minus 4%. Oh, wait a minute. I'm doing that wrong. So that would be not 20. It would be 2. Sorry. 2 divided by the square root of 100. And I get 0.2. So if you roll a 7-sided dice, which as far as I know does not exist, I guess you could probably make one. If you rolled a 7-sided dice 100 times, the average of your rolls is going to be 4 plus or minus 0.2. Okay, so the SE for average is calculated by doing the SD divided by the square root of D. So we have 3 different outcomes. We have 3 different standard errors, and we have 2 different ways to calculate the SD. Okay, and you can only use the SD shortcut when you have 2 different numbers in the box, no more. And with the 0, 1 box, it's especially easy. Okay, now, one more thing that comes out of this section is a reminder that these calculations are the same whether or not we know what's in the box. So, if we start with these boxes, then I create probabilities. There is a 68% chance that you roll a 7-sided dice 100 times and you land with an average somewhere in that window. Tuttle, that hurt your grade. You can't be on your phone. Is she cute? She's cute? Okay, well, that might be worth it then. Was it your mom? Oh. So, that is a probability. I know what's in the box. I'm predicting what will happen when I roll the dice, or when I do the draws, or when I play roulette. Okay, those are probabilities. When we don't know what's in the box, so a big question mark in there, we run around and, well, we don't. We're really bad at running surveys, right? Our data gathering systems are incredibly biased because you're only talking to people you know. And I've met some of your friends. Those people. So anyway, we just assume that we're doing everything right and we're not. And then we run the numbers. So if you don't know what's in the box, you go out there and you talk to people. And then you take what you find and you assume that that's true. And you put those numbers in the box. And then you use what you have to create SDs. And then you use those SDs to create standard errors, which are not really standard errors anymore, right? They're kind of a chance error mix, but we still call them standard errors. And then we do all the calculations in exactly the same way, and we create confidence intervals. So if I didn't know what was in this box, but I did a survey and I found 82% of the people don't like Mr. White, that might be a little low, then I pretend that's correct, I stick it in the box, I run the SD, and I end up with 82% plus or minus, let me do the calculation, so the square root of 0.82 divided by 0.18, that gives me an SD of 2.1, and then I need to know how many people I talked to. Let's say I talked to 1,000, so I divide that by the square root of 1,000, and I get 6.7%. So 82% plus or minus 6.7%. But I'm only 68% confident, so I probably want to double that. That would be 12, 13.4. So 82% plus or minus 13.4. I am 95% confident that I have captured the true percentage inside that window. What's the probability that I'm right? What's the difference between probability and confidence? Well, probability predicts something that hasn't happened yet, right? Has the true percentage of people who like me happened? Yes. It's out there somewhere. My job is to guess what that is. And I'm 95% confident that I did grab it. The probability that I'm right is either 100% or 0%. If the true percentage is in that window, then the answer is 100% probability because it's already happened. So I'm trying to guess what the true percentage is. So if you look on page 422, about 2/3 of the way down, when reasoning forward from the box to the draws, the standard error can be computed exactly from the composition of the box. So if you know what's in here, then these numbers are exact because they're probabilities. A chance quantity like the sum of the draws will be around its expected value, but will be off by an SE or so. When reasoning backwards from the draws to the box, so when we run a survey, you often have to estimate the SD of the box from the sample because we have no other way of doing it. And it takes into account how many draws you've made. So the SE itself is only an approximate. However, the interpretation of the SE is almost the same, and the math is identical. For instance, suppose the average of the sample is used to estimate the average of the box. This estimate will be off by a little, and the SE says by about how much. When the sample is reasonably large, the error in the SE itself is usually too small to matter. So that table says the SE shows the likely size of the amount off. It is a give or take number. The terminology may be a bit confusing. Statisticians speak of the standard error for the sample average. The idea is that the sample average estimates the population average, but is off by a little, and the SE gauges the likely size of the amount off. Now, we haven't totally lied to you, but I've made this, the book has made this a little bit simple. Okay? How do you know, looking at a number, if it is a standard deviation that came from the box or a standard deviation that was estimated using a sample? You guys see the difference, right? So this box has a standard deviation. I can find that from my calculator. Okay? If I don't know what's in the box, then I do a survey and I use that information to create a standard deviation, and it's probably close to this true standard deviation. But they're two different ideas. One is the true standard deviation from the box. The other is an estimated standard deviation from a sample. Well, it doesn't make sense to use the same variable for that. So in big boy and girl statistics, those two numbers actually have different variables. And the parameter average or percentage and the sample average or percentage have different variables so that you know what you're looking at. So in our introduction to statistics, this book didn't even teach them to you. In fact, it didn't teach you any symbols. I've been using symbols, the X bar and the sum. But in real world statistics, the sample average and the population average are two different letters. And the sample SD and the population SD are two different letters. So if you go on in statistics, you'll see that. But in this class, all we're doing is getting used to confidence intervals and chi-squared tests and other things that we'll be seeing. Okay, so you need to finish C and the review, and then get working on your, divide up into groups, and 1, 2, 3, 4. We're missing 4 people. So make sure that those 4 people end up in a group. Who wants to take, well, hold on, let me turn this off. Who wants to